You may have seen growth and decay in Calculus 2. There are a number of things where the rate of growth is proportional to the amount. That's what this is saying. The change in quantity with respect to time, or rate of growth, or decay, is proportional to the quantity itself. You can see a lot of investments work that way if they're compound interest, radioactive decay, and a number of other things. Now this differential equation is separable, so we can get all of the Q's on one side, all of the T's on the other side, and then integrate both sides. The integral of 1 over Q would be ln Q. The integral of K with respect to T would be K times T. And then our constant of integration. We can solve for the Q by doing the natural exponential of both sides. We can rewrite e to the kt plus c as e to the c times e to the kt, and then take e to the c and call it just a constant. So this would be our solution to the differential equation. Now we know that in the beginning t is 0, time 0 in the beginning. If we use a Q0 with subscript 0 to represent our initial quantity, then our equation becomes Q0, the initial quantity, e to the kt. The k in this case is referred to as our growth rate. So we're going to use the equation that we just derived from the differential equation to answer a typical question about the half-life. So if carbon-14 has a half-life of 5,630 years, that means the quantity at the end is half of the quantity at the beginning. And so using a 1 for the quantity at the beginning, we would have 1/2 equals e to the k times 5630. We can solve that for k and rewrite our original equation with the new value of k. And so this equation could then be used to answer any question whatsoever concerning the carbon-14. In this instance, we're asked to find the age of the artifact, that would be the T, if we have 15% remaining. So we just want the quantity Q to be 15% of the quantity Q0. So one logical choice for that would be a 1 for the Q0 and a 0.15 for the Q. And so solving for T, we end up with the age of the artifact.